Hi, and welcome to the Conditional Probability Lecture as part of the Statistical Inference class in the Coursera Data Science Specialization. My name is Brian Caffo, and this course is co-taught by Jeff Leake and Roger Pang. We're all in the Department of Biostatistics at the Bloomberg School of Public Health. So conditioning is wonderfully illustrated by this XKCD comic here. In this case, two people are standing out in a field right near a tree in the middle of a lightning storm, and one of them says we should go inside. The other one says, well, the chance of getting hit by lightning is only about 1 in 7 million, so we're fine. And the tagline is that the death rate among people who know the statistic is 1 in 6. And what the comic is highlighting is that this person hasn't conditioned on what they know, right? In this case, if you were to condition on the death rate for lightning strikes among people who were standing in fields in lightning storms near trees, would be much higher than 1 in 7 million. Let's go through another example. So a simple conceptual example. So the probability of getting a 1 when rolling a standard die is assumed to be 1/6. Suppose you were given the extra information that the die roll was an odd number, hence a 1, 3, or 5. So someone rolled a die in a way that you couldn't see, and they told you that a 1, 3, or a 5 occurred. Conditional on this new information, you would not say the probability of a 1 is 1/6 anymore. You would now say it's 1/3, equally likely between the 1, the 3, or the 5. And that's what conditional probabilities are giving you. And of course, they have a definition. So let's let B be an event such that the probability of B is greater than 0. And this is important because there's no sense in conditioning on an event that can't happen. Then the conditional probability of an event A, given that B has occurred, is written like this. The probability of A, little horizontal line B, so this is red, probability of A, given the event that B has occurred, is equal to the probability of the intersection divided by the probability of B. And we haven't talked about independence yet, but in the event that A and B are unrelated or so-called statistically independent, which we'll define later, then the probability of A given B works out to just be the probability of A. So the new information that B has occurred has given you no information about the probability law governing the event A. So let's just check that conditional probability gives us the answer that we know to be true in the die rolling case. So in our case, B was the event 1, 3, 5. A was the event 1. We want the probability of the event A conditional on the event 1, 3, or 5 having occurred. So in other words, we can say probability of getting a 1 given that we know that the roll is an odd number. That's the probability of A given B, which is the probability of A intersect B over the probability of B. In this case, A happens to lie entirely within B, so the probability of A intersect B is just the probability of A. So that works out to be 1/6, and then the probability of B in the denominator works out to be 3/6, right? 1/6 for each of the 3 mutually exclusive possibilities, which works out to be 1/3, which is what we knew had to be the answer. Perhaps one of the most famous uses of conditional probability is so-called Bayes' rule. This rule was named after a Presbyterian minister named Thomas Bayes, who had his work published posthumously. Bayes' rule allows us to reverse the role of the conditioning set in the set that we want the probability of. So imagine in the event that we want the probability of B given A, when we have or can easily calculate the probability of A given B. Well, Bayes' rule says you can do that. You can relate B given A to A given B, but you need some other information. You need the probability of B marginalized over A. And this is quite useful in the sense of diagnostic tests, and we'll go over some examples here in a minute. So let's talk about conditional probability in the context of diagnostic test, one of the most important examples of conditional probability and Bayes' rule. Let's let plus and minus be the event that the test is positive or negative. Let's think of a test for a disease. So plus being that the test says the person has the disease, and minus being that saying that they don't. And then let's let D and D complement be the event that the person either does or does not have the disease, respectively. Then the sensitivity is the probability that the test is positive given that the subject actually has the disease. This would be a marker of a good test. You would want the sensitivity to be high. The specificity is the probability that the test is negative given that the subject does not have the disease, probability minus given D complement. Again, you want the specificity to be high for a test to be good. And notice in the development of diagnostic tests, these things are at least conceptually attainable. There's, of course, a lot of difficulties in finding good sensitivity and specificity estimates. But for example, in an HIV blood test, you could take people who you know to have the disease and apply the diagnostic test to that blood. You could also take people who you knew for sure did not have the disease, and you could apply the diagnostic test to the blood samples from those subjects. If you happen to have a positive test, the number that is most of concern to you is the probability of having disease given that positive test, the so-called positive predictive value. If you have a negative test, you're interested in the probability of not having the disease given that negative test, the so-called negative predictive value. We might say in the absence of a test, we might say the probability of having the disease is the so-called prevalence of the disease. I always like to talk about diagnostic likelihood ratios because in nearly any introductory or advanced class on this stuff, they tend to be left out, and I quite like them. So the diagnostic likelihood ratio of a positive test is the sensitivity over 1 minus the specificity, and the diagnostic likelihood ratio of a negative test is 1 minus the sensitivity over the specificity. And I'll go over in a minute why I think these are incredibly useful numbers. Let's go through an example. A study comparing the efficacy of HIV test reports on an experiment which concluded that the antibody tests have a sensitivity of 99.7 and a specificity of 98.5. So these are kind of made up numbers, so don't think of these as cardinal truths about antibody tests for HIV. Suppose that a subject from a population with a 0.1% prevalence of HIV receives a positive test result. What is the associated positive predictive value? So mathematically, we want the probability of disease given a positive test result, given the sensitivity and the specificity, and the prevalence, P of D, 0.001. So let's plug directly into Bayes' rule. We want probability of disease given a positive test result. That's the probability of the positive test result given disease times the probability of disease divided by this denominator right here. And again, it's not immediately clear where the numbers from the problem are coming from here, but let's just note that the probability of a positive test result given that the person does not have the disease is 1 minus the probability of a negative test result given that the person does not have the disease, or that's 1 minus the specificity. And the probability of disease complement is 1 minus the probability of disease. Now we've rewritten it only in terms of things that we know, and we can just plug in the numbers and get 6% as our probability. So in this population, a positive test result only suggests a 6% probability that the subject has the disease. So in other words, the positive predictive value is 6% for this test. The low positive predictive value in this case is largely due to the low prevalence of the disease. However, imagine in the process of counseling this person about their positive test result, the counselor learned that the subject was an intravenous drug user that routinely had intercourse with an HIV-infected partner. They would assume then that the relevant prevalence for this person was much higher, and thus the positive predictive value was much higher. I want to now distinguish between the component that is dependent on this prevalence and the component that is what I would describe as the objective evidence of the positive test result. And that's what the diagnostic likelihood ratios are, and that's what we'll cover next. Here I just give the formula for the positive predictive value again as it's plugged into Bayes' rule. And remember, this formula then only depends on the sensitivity, 1 minus the specificity, and the prevalence of disease. We can do the exact same thing for 1 minus this probability, 1 minus the positive predictive value, which is the probability of not having the disease given a positive test result, and you get this formula to the right. Notice that the denominator is identical in either of the two probabilities, and the numerator changes. So keep that in mind for the next slide. So if we were to divide these two equations, we get the following. the probability of disease given a positive test result divided by the probability of not having the disease given a positive test result. Whenever you take a probability and divide it by 1 minus that probability, you get the so-called odds. So here on the leftmost side, we have the odds of disease given a positive test result, and on the rightmost side, we have the odds of disease in the absence of the test result. Here, this factor in the middle is the diagnostic likelihood ratio of a positive test result. So the equation is the pre-test odds of disease times the diagnostic likelihood ratio equals the post-test odds of disease. So in other words, the diagnostic likelihood ratio of a positive test result is the factor by which you multiply your odds in the presence of a positive test to obtain your post-test odds. And then similarly, DLR minus relates the decrease in odds of disease after a negative test result to the odds of disease prior to the test. So it's a very similar calculation. So let's go through our example. Suppose that a subject has a positive HIV test. If we calculate using our sensitivity and specificity from before, the diagnostic likelihood ratio works out to be 0.997 divided by 1 minus 0.985, which works out to be 66. In other words, no matter what your pretest odds are, you multiply them times 66 to obtain your post-test odds. Or in other words, the hypothesis of disease is 66 times more supported by the data than the hypothesis of no disease. Now, if the pretest odds are very small, then still multiplying them by 66 will result in a still small number, though 66 times larger. Let's just very quickly go over an instance when a subject has a negative test result in using the DLR minus. So in this case, the DLR minus from the sensitivity and specificity given before is 0.003. So therefore, your post-test odds of disease in the light of a negative test result is now 0.3% that of the pre-test odds of the disease. Or in other words, the hypothesis of disease is supported 0.003 times that of the hypothesis of the absence of disease given the negative test result. And I should note that it's simply convention that both the DLR plus and the DLR minus are specified in the terms of having the disease in the numerator of the odds calculation. Let's cover briefly the subject of independence. We alluded to this earlier in that we said that A is independent of B if the probability of A given B is equal to the probability A for an event B that has positive probability. Another definition of independence is that the A and B are independent if the probability of A intersect B works out to be the product of their probabilities. This then begins a very important lesson. You can't just multiply probabilities willy-nilly. You have to multiply independent probabilities associated with independent events. Let's go through a numerical example. What is the probability of getting 2 consecutive heads? Well, let's define A as the probability of getting a head on flip 1 and B as the probability of getting a head on flip 2. Both probabilities are 0.5. In this case, we're assuming a fair coin. A intersect B is the event of getting heads on flips 1 and 2. In this case, because the events are independent, the probability of A intersect B is the product of the probabilities, and so we would say that it's 0.25. People do this calculation rather naturally. The problem is when people multiply probabilities when they shouldn't. A particularly stark instance of incorrectly multiplying probabilities occurred in volume 309 of Science, which was reporting on a physician who was on trial for giving expert testimony in a criminal trial. The criminal trial involved a mother who had had 2 children die from sudden infant death syndrome. The expert testimony took the prevalence of sudden infant death syndrome as 1 out of 8,500 and then multiplied them together to find the probability of 2 children having sudden infant death syndrome with the same mother. Based on this evidence, and I presume other evidence, the mother on trial was convicted of murder. Relevant to this class, the principal mistake was to multiply probabilities for events that were not necessarily independent. And it makes sense that in this case to assume that the events would be dependent because any biological process that has a genetic or familial environmental component is likely to be dependent within families. In this class, the main way we're going to use independence is that we're going to assume that a collection of random variables are independent and from the same distribution. We call such random variables independent and identically distributed. So you might think of several coin flips as IID because they're independent. One coin flip is independent from the next one, and they all arise from the same distribution, 0.5 for heads and 0.5 for tails. IID sampling is our default model for a random sample. So whether we have an actual random sample or not, we often use random sampling or the model of IID as a conceptual model to analyze our data. It'll be our principal mode of analysis for this class.